Hi everyone, I'm glad to present our work titled Behind the Wheel, Enhanced Indoor 3D Scene Reconstruction with Occluded Surface Completion at CVPR2024. Given the depth sequence with camera poses, depth fusion methods such as BNV fusion and TS depth fusion have showed impressive results in scene-level 3D reconstructions. However, these prior methods only focus on the reconstruction of the visible areas in the scene, neglecting the invisible areas due to the occlusions. For example, the contact surface between furnitures, occluded wall and floors. In this work, we tackle a novel but challenging task of completing the occluded scene surfaces, resulting in a complete 3D scene mesh. Our method enables more accurate 3D modeling of furnitures and reconstruction of furniture-obscured room regions, significantly advancing indoor scene reconstruction. The success of our method lies upon a hierarchical octree representation of the scene, coupled with a special design of a dual decoder architecture, which jointly reconstructs the complete 3D scene geometry. We design a learnable hierarchical octree as implicit scene representation. We use fine-level features and coarse-level features within the octree to separately represent the visible and occluded regions. Fine features are expected to encode high-frequency detailed geometry of visible surfaces, while coarse features are expected to represent contextual structural information, which is more generalizable for occluded surface completion. Besides the hierarchical feature, we designed a coupled dual decoder, including a scene-specific visible decoder and a generalizable cross-scene occlusion decoder. The visible surface decoder with fine-level features is optimized online using depth readings in the testing scene, while the occluded surface decoder with coarse-level features is trained offline with multiple scenes. To address the limitations of existing public indoor RGBD datasets, which typically lack complete 3D meshes of room scenes and furnitures, we developed a 3D complete room scene dataset named 3D-CRS. The 3D-CRS dataset features 20 high-quality indoor scenarios. Each scene includes RGBD images, camera poses, complete 3D scene meshes, including both 3D furnitures and room layouts. Given the sequence of depth readings, we construct a L-level octree and store latent features at 8 corners per octree node in each level. For a query point, we retrieve its feature vector by trilinear interpolating its corresponding corner features. We divide the octree features into coarse features in the high-level layer and fine features in the low-level layer. We feed the visible decoder by concatenating low-level features and the invisible decoder with high-level features. The pipeline of our method has 3 stages. We refer the visible surface decoder as geodecoder and the invisible surface decoder as 3D implanter. At the first stage, we train our 3D implanter across scenes. At the second stage, we jointly optimize geodecoder and feature on the new testing scene. At the third stage, we generate 3D surfaces on the testing scene. At the first stage, we use 3D complete scene meshes from multiple scenes to train a generalizable 3D implanter. We first convert point clouds unprojected from given depth maps of each scene into octree volumes. We train our 3D implanter in a cross-scene manner, using points and their ground truth sign distances sampled from complete 3D meshes of n training scenes. At stage 2, as the depth measurements are available in the testing scene, we sample points along the camera array and calculate their side distances. We use these samples and supervision to optimize geodecoder with fine-level features for visible geometries. We also optimize coarse-level features through the frozen 3D implanter, which is used to infer the occluded geometries. At stage 3, we uniformly sample points in the 3D space of the testing scene and apply a criterion to determine whether the points belong to visible or invisible regions. We then feed the classified point and its retrieved feature into the corresponding decoder to infer SDF value. We use marching cubes to produce the final triangular mesh. Results show that our method outperforms the baseline significantly, particularly for the completance and F1 scores. Completance depicts the surface completeness levels. Our method achieves a much higher completance score than the baselines because it reconstructs the 3D surface of occluded regions, while the baselines fail to do so. Visualization results show that the baselines could only reconstruct the surfaces of visible areas, failing to complete the surface of occluded areas. In contrast, our method reconstructed the accurate and smooth 3D surface of both visible and occluded areas, particularly evident in areas like the backside of the sofa and the floor under the furniture. These visualizations demonstrate that our method achieves more complete 3D surface reconstructions, while the baseline tend to leave many incomplete areas. We investigate how varying the number of available depth frames per scene impacts the performance of our method. As the number of depth frames is reduced, the occluded regions increase. For the baselines, their completance score largely decreases. However, our completance score remains steady with only a slight drop, even with a very limited number of depth frames. We highlight the effectiveness of the 3D inpainter, specifically trained across various scenes. Without cross-scene training, completance shows a much lower score than our floor method. This also confirms that only a well-trained 3D inpainter can accurately predict occluded surfaces. We show room layouts after furniture removal on the 3D CRS dataset. Room layout results generated by the baseline methods contain many large missing areas. In contrast, our method provides a complete room layout surface without obvious missing regions. We also qualitatively demonstrate our method's adaptability to real-world dataset ScanNet. Thank you for watching this video.